Hello and Assalamualaikum warahmatullahi wabarakatuh. Today, we would like to present our chosen carbohydrate, which is lactose, as the disaccharides. Disaccharides are carbohydrates formed when two monosaccharide units are joined together by a glycosidic bond. One common example of this class is lactose, which is naturally found in milk and dairy products. Lactose consists of two simple sugars, glucose and galactose, and it plays an important role in human nutrition, especially as a source of energy. In this presentation, lactose will be used to represent and explain the key characteristic of disaccharides. Disaccharides such as lactose are important in the human diet because they serve as a source of energy after being broken down into their monosaccharide components. Lactose is particularly significant for infants as it supports growth and development during early life. It also helps improve calcium absorption, which is essential for bone development. In addition, lactose is widely used in the dairy and food industry, and its importance is further highlighted by health conditions such as lactose intolerance, where the body has difficulty digesting it. Structurally, lactose is a disaccharide with the chemical formula of C12H22 and O11. It is composed of two monosaccharides, which are beta-D-galactose and D-glucose. These two units are linked by a beta-1,2,4 glycosidic bond, where the anomeric carbon of galactose is connected to the fourth carbon of glucose. In the Fischer projection, the linear arrangement of atoms allows us to clearly identify each monosaccharide unit. When represented using the Haworth projection, the cyclic structure of lactose becomes more apparent, making it easier to visualize the glycosidic linkage due to the presence of a free anomeric carbon in the glucose unit. Lactose is classified as a reducing sugar. This is the ball and stick model for lactose.
Now I will explain the physical and chemical properties of lactose. Physically, lactose is a white crystalline solid that is naturally found in milk and dairy products. It has a low sweetness intensity compared to sucrose, which means it tastes less sweet. Lactose is also soluble in water, allowing it to dissolve easily in biological system and food processing application. Chemically, lactose is classified as a reducing disaccharide because it contains a free anomeric carbon. This free anomeric carbon allows lactose to participate to redox reactions. The two monosaccharides unit in lactose are linked by a beta-1,4 glycosidic bond, which plays an important role in determining its chemical reactivity. Let's look at the biological role of lactose. Lactose is the primary carbohydrate present in mammalian milk and serves as an important source of nutrition for infants. After digestion, lactose provides metabolic energy, supplying approximately 4 kilocalories per gram. In addition, the breakdown product of lactose helps support the growth of beneficial gut microbiota. This contributes to healthy digestion and nutrient absorption, especially during early stages of development. Now, I will explain how lactose is synthesized. Lactose is naturally synthesized in the mammary glands of mammals during milk production. It is formed from two monosaccharides, which are glucose and galactose. This reaction is catalyzed by a specific enzyme known as lactose synthase. The synthesis occurs through a condensation reaction where a water molecule is released as the glycosidic bond is formed. This enzyme control process ensures that lactose is produced efficiently and accurately.
Now, I will explain the applications of lactose in different industries. First, in the food industry, lactose is widely used as a natural sweetener with low sweetness intensity. It also contributes to the Maillard browning reaction, which helps improve color and flavor in baked and heat-processed foods. In addition, lactose acts as a fermentation substrate for lactic acid bacteria in yogurt and cheese production, supporting probiotic growth and food preservation. Next, in the pharmaceutical industry, lactose functions as a filler, binder, and carrier in tablets, capsules, and dry powder inhalers. It is preferred because it is chemically stable, non-toxic, and easy to compress, ensuring uniform drug distribution and accurate dosage. Lastly, in biotechnology and sustainable applications, lactose derived from dairy waste is used as a carbon source in microbial fermentation. It can be converted into value-added products such as lactic acid, bioethanol, and galacto-oligosaccharides. This supports green chemistry and reduces environmental pollution from dairy waste. Moving on to the health implications of lactose. In terms of nutritional value, lactose provides metabolic energy for about 4 kcal per gram. It enhances calcium and magnesium absorption, which contributes to bone mineralizations and dental health. Lactose also plays a role in maintaining a healthy gut microbiota through fermentation products. However, lactose can also pose health risks, particularly lactose intolerance, and this condition occurs due to lactose enzyme deficiency. Undigested lactose undergoes fermentation in the colon, causing symptoms such as bloating, diarrhea, and abdominal discomfort. The prevalence of lactose intolerance is especially high among Asian, African, and South American populations. On a global perspective, increased awareness of lactose intolerance has led to dietary restrictions that may reduce calcium intake. If not managed properly, this can increase the risk of osteoporosis. Therefore, lactose-free dairy products are recommended instead of total dairy avoidance. Recent research focuses on converting lactose into bioactive compounds and functional ingredients. One example is galacto-oligosaccharides, which act as prebiotics that promote beneficial gut bacteria such as bifidobacteria. Lactulose is another derivative used therapeutically for constipation and hepatic encephalopathy. In addition, lactose is being explored in drug delivery systems, particularly for pulmonary drug delivery and nanoparticle-assisted formulations. These innovations improve drug stability and enhance targeted delivery efficiency. Finally, in sustainable bioprocessing, where lactose is converted into bioplastic precursors and biodegradable polymers. This supports the circular economy and reduces industrial waste, making lactose a valuable resource beyond nutrition.